So thanks so much for inviting me to talk. So the work that I'm going to be presenting is on pointer-sentinel mixed models with a number of my colleagues from Salesforce, including Kaiming Zhong, James Bradbury, and Richard Socha. So you just heard kind of the importance of language modeling for a number of different tasks, including machine translation, speech recognition, and even to things like question answering, which you wouldn't necessarily consider kind of the standard for what language models might do, or query completion. But there are some pretty huge issues when it comes to recurrent neural networks, which kind of hold state of the art for these language modeling data sets. The three big things I'm going to be talking about is hidden state is a huge limitation for the capacity of these networks. So these recurrent neural networks do best when they have huge hidden states, but when you increase the size of the hidden state, the parameter size increases quadratically. So you're either going to run out of memory or you're going to have a very poor time training these things the larger you make them, even though that's exactly what you want to get the best results. There are a few attempts at things like attention, where you can kind of use previous outputs, but the issue with this is that it hasn't been highly effective for language modeling previously. There's also an issue of vanishing gradients that kind of still hinder previous learning. We like to think that LSTMs have solved this long-term dependency problem, but most of these language models actually only train BPTT for the last 35 time steps. And many sentences are going to be longer than 35 time steps, so it's really quite limited if you think in terms of, say, articles or things like that. And the third one, and main thing that I'm really attending to in this work, is encoding and decoding rare words is still highly problematic. And in real life, the majority of the words that we're interested are in the long tail. If you can get a sentence that's primarily going to work, but say misses the name of the person that the article is about, that's really not a good use case for most people. This also leads into some other interesting problems. So the idea that word vectors need to actually get in sync with the softmax weights. So when you're doing language modeling, a lot of the time, all it's doing is spending a lot of energy learning this one-to-one mapping, which you can imagine is not an efficient use of time, given that we already know exactly when those things line up. And the second is that when we have very few examples of these words in the long tail, actually learning to encode and decode them from the hidden state is problematic. And the third one is that nothing can really be done when it comes to these out-of-vocabulary words we might run into. If it's a last name that is difficult to, or very rare, humans wouldn't have a problem with that if they've just seen it in the previous sentence, but our models have no way of actually handling this at all. So a lot of this work is based around an extension of pointer networks. So a quick introduction to them is that ideally, if we have a vocabulary that's far too large, but we're really only interested in things in the input, we should avoid actually having a vocabulary at all. So in the case here, we want to produce a convex hull for this object up here, and we have 4 different points that we end up reading through. And one way you could do it with sequence learning is throw in each of these points in turn, and then have the sequence learning spit out at the end the ordering of the original inputs, so 1, 4, 2, 1. The issue is that all means all of that information needs to be encoded in the hidden state, and it needs to remember basically the ordering of things as they were passed in, which in this situation doesn't actually make sense because you could swap x2 and x3 or so on. So instead, what pointer networks do is they basically have an attention layer. They have what you could consider a query that applies attention over it, and the word or the token with the maximal attention is the one that you end up outputting. And so in this case, it's the same sort of thing, except it no longer has to actually encode these points in the hidden state itself. And it can output the exact original point because all it's doing is pointing to the input and saying output that. And this has worked incredibly well for some very interesting and non-standard tasks. So things like convex hull, where the LSTM in the top left does terribly, but the pointer network in the bottom left does quite well on a far more complex task, and even things like traveling salesman's problems. And so again, the main point of the pointer networks is that we can avoid needing to learn to store the actual identity of these tokens in the hidden state itself. And this means it works quite well on limited data and also on rare tokens. And this might help us solve in this kind of rare and out-of-vocabulary problem, except that language modeling, a lot of the time, the words aren't actually in the input. The other thing that's quite interesting about pointer networks is that they provide a direct supervision to your task. They tell you exactly where you need to look. So if we were talking about the name example before, if you know that the next word coming up is social, and the input had SOCIA somewhere in it, the pointer network tells you immediately exactly where in the input you should actually be pulling information to or directing a gradient to. And so it helps with the gradient flow by providing this shortcut rather than having to force the neural network to traverse the full path through the RNN to that point. So what we want to do is we want to somehow merge the RNN and the pointer to enable us to have these kind of two different advantages, the generation capability of the vocabulary softmax and this out-of-vocabulary advantage that the pointer model has, or we can also think of it as like a positional softmax. So this is not a new idea. Gulcheri et al. Also had a version of this where they use a switch network that will actually use the hidden state of the RNN to decide whether or not you should use the vocabulary or the pointer network. The major issue with that is that all of that relevant information needs to be encoded in this hidden state. And the hidden state, as we mentioned before, is very limited. And if you keep scaling it, it makes everything slower. And if you think about what's needed for the pointer network itself, you want to probably encode things like the word and the position as you move along the window, and also keep updating those, because at some point, if you've, say, got a window of only 100 words long, it's going to fall out the end of the window. So all these things would need to be encoded in the hidden state, and that's kind of suboptimal. So our suggestion is the idea of a pointer sentinel. So the idea is you run the pointer network as usual, except you add in one extra term, which we refer to as a sentinel. If the network isn't confident, what you can do is you can basically put all of the weight on the sentinel, which says, OK, give all this probability mass to the normal RNN softmax vocabulary. And in that way, it basically falls back to a mixture model where, if the pointer network is highly confident, it can push all of its weight into the pointer network. And if it's not confident, it can back off to the vocabulary. So to reiterate one of the other things I mentioned earlier, we keep saying LSTMs do well for these long-term dependencies, but they generally only do BPTT for 35 time steps. And it is slightly even worse than that, in that when you have this window of 35 words that you're going to be doing BPTT for, the first word in that window actually doesn't have any history that it can modify. It can only modify the word vector itself. So it's really quite an inefficient way of doing this. So we also train it slightly differently. We only have one supervision signal all the way at the end and run through the full length of the window. So for our experiments, we were looking at datasets. And one of the standards is Mikolov's Pentree Bank, as you guys have recently seen. It's a standard benchmark for a lot of this sort of stuff. And it's also article level rather than sentence level, which is a big thing when you want to try and modeling these longer term dependencies. 1 billion word LM is language modeling dataset is sentence level only. But there are some issues with it. So one is that it's small both in the size and also the vocabulary. So as earlier mentioned, it's 10,000 words in size. It's also all lowercase, there's no punctuation, numbers are replaced with n. It's not really realistic in a lot of different tasks. So we looked at tackling this by introducing Wikitext. Basically, we took entries from high-quality Wikipedia articles, and we ensured the vocabulary was quite large. So we only converted a token to UNC if it occurred less than 3 times, similar to 1 billion language modeling dataset. And we kept numbers, capitalization, and punctuation as well. And I also quite like it because it has things like Super Mario in it. So as far as a dataset comparison, we made 2 different versions of Wikitext 2. One is about the same size as Pentree Bank, and the other is 100 times larger than Pentree Bank, or 1/10 the size of 1 billion language modeling dataset. And they both had the same validation and test set, whilst having far more realistic vocabularies. So it actually has this long tail. So first, the results for Pentree Bank. There is a lot of previous work, a lot of interesting work. We're primarily interested in kind of the most recent work, and specifically results that get similar accuracy, similar perplexity to us, but with similar model sizes. And the kind of most interesting thing for me is the zone-out variational LSTM, standard LSTM, and you add the pointer sentinel. It adds about 1 million parameters, so a very small addition, but there's about 10% drop in perplexity. And this could also be chained onto different underlying recurrent neural network cells, such as variational RHN and other things like that. If you then run this on Wikitext 2, which has the kind of more realistic data set, although it's about the same size as Pentree Bank, the drop in perplexity is even better, and primarily motivated by the fact that it's a more realistic vocabulary, and that's where the pointer sentinel actually does well. Here we have the most frequent, basically bucketing of the vocabulary, so most frequent words on the left and least frequent words on the right. And you can see that the gain in perplexity is far better for these rare words. So it's basically saying if the word is rare, you're going to be doing better with it on the pointer model. And this progress is all continuing. So independently, Facebook came up with a continuous cache, which is a similar mechanism as the pointer Sentinel. And they also reported results on PTB, Wikitext 2, and Wikitext 103. So I'm very glad it's already being used. There's also tying word vectors, which helps with this rare words problem. And there's also continuing improvements on these basic RNN cells, so recurrent highway networks, and also neural architecture search with reinforcement learning. And very briefly, is some interesting examples. So as I mentioned before, for rare named entities, it does quite well. It basically is able to recall into the past exactly where it should. And surprisingly, also actually for even frequent words, uses a pointer. So things like billion or words like said, which are really frequent, it'll still use a pointer to actually help in deciding what to use. So in conclusion, the pointer Sentinel mixture model allows you to basically improve both perplexity and rare and out of vocabulary word handling at a minimal cost in terms of parameters. And when using these kind of recurrent neural networks, I'd highly recommend thinking about like both, I guess, standard training and also the data sets that we use and whether there are potentially issues with it. And finally, if you are doing these kind of long-term dependency or long-tail language modeling challenges, I highly recommend you check out Wikitext 2 and Wikitext 103. Thank you so much.
Thank you, Stephen. Any question?
So I heard a different technique of handling out of vocabulary words is like embedding their context and trying to use that. Can you compare with that at all?
You could. I guess there are a number of variations of this sort of thing. People have considered running essentially word2vec or similar sorts of things basically in real time in prediction step as well. And these all could work. There's also basically constructing the word vector from the actual constituent characters themselves. So there are certainly a lot of different ways we could be handling this. I guess this is a word level consideration of it. But it's still, I guess, a very open problem. I don't think anyone can happily say that they've solved it or have a consistent solution that scales well. Yeah.
Thank you.
Thanks.
Let's thank the speaker.